Okay, so I will draw the problem it again. So it is my, sorry, I am drawing the free body diagrams. So it is my AY, it is AX, this is BY. 30 kilonewton load is acting and a uniformly distributed load of 3.75 kilonewton per meter is acting. Correct? This is my point A, this is my point C, and this is my point B. This is 1 meter, this is 2 meters. Now what I am taking, case 2, that I am taking a section in between these 2 points. So this is my point X at, suppose I am keeping the name as same, at X distance from the support. Okay, now this X is, so this is my X distance from the support. And now the case 2 is, I will write case 2 is X, now it is greater than 1 meter, greater than or equal to 1 meter, and less than or equal to 3 meters. So X varies from point C to point B. So this is my case 2, right? Correct? So similarly we can solve the equation. Okay, similarly we can solve the equation. Let us solve it. How it will be? So if I draw the, you can say free body diagram for this. So this is my AY, AX equal to 0 already I know, so no need. I have a 30 kilonewton load here at 1 meter at X distance. Suppose this is my X. Okay, at point, this is my point X. Okay, so now we have shear here at this point. So I have Vx, and again at the load is acting this direction, so I will be having a moment of Mx here. Correct? Mx here, I will write this point somewhere here, X point. Okay, it is for case 2, and also this distributed load of 3.75 kilonewton per meter. Okay, so now what we will do, if you see the similar way, we will use the equations of equilibrium. So if I just do it here, summation of Fy equal to 0, I can say that Ay minus Vx because it's a downward direction, load is also acting downward direction, so minus 30 minus, so this is my 3.75 acting at the center of X by X, so X by 2, and total load is 3.75 into X. Okay, so it is acting 3.75 into X total load, so 3.75 X, this equal to 0. Correct? AY value we know 25.625, we can directly put it here, so it will be 25.625 minus Vx minus 30 minus 3.75x equal to 0. From here, if you find out Vx, it will become how much? If you see 30 minus 25.30 minus 25.625, it is 4.375, and if you see here 4.375, it will be plus, then this Vx is minus, suppose this is minus, so it will become plus 4.37. I'm taking in that direction, right hand side, 375, and this will become plus 3.75 into X. Correct? Now if I just remove this symbol, so now it will become negative, it will also become negative. Okay, so this is my equation Vx equal to, suppose this is equation number 5. This is equation number 5. Correct? Now another equation we can create, again moment about x equal to 0. So summation of mx equal to 0. So we are saying how much we can see it. First of all, direction of moment minus mx, then minus, so this is 1 meter, 30, this 30-meter load will create a anti-clockwise moment, correct? So minus 30 multiplied by, it is acting at this distance, so which is x minus 1. Okay, so 30 into x minus 1, again minus, say this uniformly distributed load acting at the center of the this x distance as the equivalent load. So this equivalent load is acting here at x distance, x by 2 distance from here, correct? It is 11.25 if you remember. Sorry, not 11.25. It is will be 3.75 into x. Okay, so it is 3.75 multiplied by x. Okay, so I would write it here as 3.75 x acting at x by 2. Fine. So equal to 0. Now if I just find out one more thing I think I have missed. Yeah, if you see one more component is there, this ay. It is also acting a clockwise moment at mx, so it will be ay into x. I would write it here. So plus ay into x equal to 0. Correct? So minus mx minus 30x plus 30 minus 1.875 x square. Okay, and plus ay, so plus 25.625 x. This ay, it is nothing but 25.625 from the previous equation 2, I guess. So this equal to 0. This equal to 0. Correct? Now if you find 30x minus 25.625x, it will be 4.375x as we have seen earlier. So what are the things we have to see? Minus mx equal to, this 30 will go that side, so minus 30. Then we will have minus 4.375, so it will become plus 4.375 x, then plus 1.875 x square. Correct? Okay, if I remove the minus from here, so this will be plus, this will become minus, and this will also become minus. Correct? So this is my equation 6. Correct? So these are the equations we have now. Okay, now what we will do, we will draw the bending moment and shear force diagram. I am still confused whether I have done this particular thing correct or not. Please do let me know in the comment if it is correct. I feel it is correct, but when I have solved it previously, there's something mistake I have done in the sign convention. So that means let's see if our results are correct we are getting. So now I will draw the beam support. Okay, we have a roller support, we have a 30 kilonewton load here, and we have a uniformly distributed load due to self weight is 3.75 kilonewton per meter. Okay, and now if we draw, see, if you remember in the colleges we used to draw bending moments like this. at the bottom of the problem itself, like this. First we will draw the shear force diagram, suppose. So at x equal to 0, so this is my 0, this is my 3 meter, correct? A, B and C. As at x equal to 0, when x equal to 0, which equation we will be using? It is between point A to C. Okay, so x is greater than 0 and less than this 1 meter. Okay, we know this is 1 meter and this is 2 meter. Okay, if you want to write, you can write it there also. This is 2 meter. Okay, if you remember this case 1, x is greater than 0, greater than or equal to 0, less than or equal to 1 meter. In this case, Vx formula we got 25.625 minus 3.75, x equation 3. So from equation 3, what we got? 25.625 minus, if you see here, 3.75 x. So 3.75 x here multiplied by, now I will put the value of x, which is 0. Okay, so how much we are getting? So this will be 0, so we are getting 25.625 kilonewton. If you remember, we found out ay and the same value we also got in ay also, which is 25.625. So you can see the applied reaction that we are getting, that is the load, and the I can say shear force, it will be the same. Now the value of shear force is positive, so the force also acting upwards, so obviously the shear force direction also positive we are getting. So I hope you understand how we got this positive. So this is my beam, so I have got a positive value of shear force here, which is 25.625 kilonewton. Okay, now at this 1 meter, as there is one more point load at this particular point acting, so at x equal to 1 meter, again the same formula we will be using, and it will be 25.625 minus 3.75 multiplied by 1. Okay, so the answer will be, if you see, 25.625 minus 3.75, so it is around 21.875. so 21.875 kilonewton. So we will be getting a value of, suppose somewhere here, which is 21.875. so we got a diagram like this here, correct? In between we do not have any point load, this is a uniformly distributed load. So directly if we find at this point x equal to 3, now for x equal to 3 we need to go for this case 2. For x equal to 3, Vx equal to this, okay, minus 4.375 minus 3.75 into x. So if I write it here, so these are from equation 3. Now at x equal to 3, I will write from equation, which one? Equation 5. So from equation 5, what we are getting, if you see, minus 4.375 minus 4.375 minus 3.75 into x, 3.75 multiplied by x. Okay, so if I put x equal to, if I just remove the x, this x equal to, x equal to 3, so how much we will be getting? We will be getting a value of minus 4.375 minus 3.75 into 3, 3.75 into 3. So we are getting a value of 15.625 minus 15.625 kilonewton. So this minus is giving me the direction. Okay, so that means the direction will be downwards. So it will be somewhere here. Okay, this value, which is 15.625. Now if I just, okay, one more thing I should get actually from this equation, that at point 1, using this equation, if I find at point 1 what will be the you can say shear force. So if this equation I use from 1 to 3, at x equal to 1, how much we are getting? If you see, 4.375 minus 3.75 into 1, so minus 4.375 minus 3.75 multiplied by 1. This equation also we need to use 1 because this is a common equation for this point. So it will be how much? Minus 4.375 minus 3.75. So how much we are getting? Minus 8.125. So I will write minus 8.125 kilonewton. So that means at this position, for this equation, we are getting a value of 8.125. Minus is showing me the direction. Okay, so I will just add this. So this is my, if I just mark it like this, so this is my shear force diagram for this particular loading. Correct? This is my shear force diagram, this particular loading. So I will write SFD, shear force diagram. Now let us find out the bending moment. First thing, we all know, as this 30 kilonewton load acting at this particular point is the governing load. If you see 3.75 into 3, we are getting 11.25. Okay, so if it is only uniformly distributed load, you would have seen that we are getting a parabolic curve for the loading, for the bending moment. But as this point load is a governing load and very much higher than the uniformly distributed load, so in this case also we will get a bending moment expected for this point load, which is a triangular load, triangular moment, you can say value. Okay, triangular moment diagram, I should say. So we will see from these equations. Okay, to see this equation, first I would say at, okay, this is for shear force. I will write the same here for moment. So suppose this is for shear force, and I will write this BMD, bending moment diagram. So at x equal to 0, obviously it is a simply supported beam, and we should get bending moment also 0. Correct? So I will use the case 1, and I have this moment mx equal to, okay, 25.625x minus 1.875 x square. So case 1, right? This one is case 1. So I will just write 25.625 x minus 1.875 x square. Okay, very simply, this is also 0, this is also 0, so obviously we are getting finally 0. So the bending moment diagram, bending moment at this end is 0, obviously, no doubt, no need of this, it is just a silly explanation, no need, not required at all, but still if you want you can see like this. So this is my point here, the bending moment is 0, so there will be no moment. Correct? At this point we expect that this point we will get some value because it is a, this is the governing load here, 30 kilonewton. So at x equal to 1, If I add it, so how much it will be? 25.625 into 1 minus 1.875 into 1 square. So how much we are getting? How much we are getting? So it will be 625 minus 1.875. It is equal to 23.75. So I should write 23.75 kilonewton meter is my moment value. So it is positive. So somewhere here at this point I am getting a value of 23.75 kilonewton meter. Okay, let it be like this. Now again there is no point in any other point load, so we will find out at the x equal to 3. So at x equal to 3, sorry, at x equal to 3, okay, so these two we got from equation, I should write it actually for your reference, from equation 4. Okay, these two we got from equation 4. Now this one we will get from equation if you see this one, yeah, equation 6. So from equation 6, if you see here, so it is 30, so I should write it here, 30 minus 4.375 into 3, 4.375 multiplied by 3 minus 1.875 into 3 square. So 1.875 multiplied by 3 square. Correct? So how much we are getting finally? So you can see here 30 minus 4.375 multiplied by 3 minus 1.875 multiplied by 3 square. 3 square, yeah. So ultimately we are getting answer as 0. So that means obviously it is again a simply support. So we will get an answer, a bending moment, which is 0 here. So that means our bending moment diagram will be something like this. Okay, so this is my bending moment diagram. If there is only uniformly distributed load, I would have drawn this you can say diagram as a parabolic diagram. Okay, though this equation you can see ax square plus bx plus c, no, this is not an equation of parabola, right? Parabola is y square plus ax, something like this, right? So we are not getting an equation for parabola here. So this is how we got the BMD now. So BMD as per our manual calculation. I hope this how this manual calculation is done you understood. So actually we place this value multiplied by 3 multiplied by 3 square and we got a value of 0. Okay, fine. Here what we done, multiplied by 1 multiplied by 1 square. Fine. Okay, so this is my value and shear force bending moment diagram as per the manual calculation. Very simple basic calculation, step by step we have done. Now let us go to the software. So I will just open STAAD.Pro. I will create a new project. So new, suppose substructure 2, I will metric and create. Now first of all I need to create the nodes. So what I will do, I will create a node first, 0. I got a node, I will translate this. I need 2 steps along x direction. The first one will be at 1 meter, second one will be at 2 meter, correct? sorry, first one will be at 1 meter, second one will be at 2 meter. I will click on link steps. I'll click on OK. I think it is correct, right? If I just see the sorry, if I just see the node to node distance, so this is 1 meter, this is 2 meter. Okay, fine. So I will just clear it or let it be here. Now what I will do, I will assign a property and the support. I'll go to property. Our property was 300 by 500 RCC beam, correct? So I'll define, I'll go to rectangle. My depth is YD, which is 500 mm, 0.5 meter, and 300 mm is the width, 0.3 meter. Concrete is the material, and click on add. And I will assign this here. Assign to selected beam, assign. Now at this point I have a pinned support, so I'll go to support. I'll create a support. I'll go to pinned, add, and at this point I have a roller support which is translating along X direction. Okay, it is moving along X direction. I'll create, I'll go to fixed but. So I want to release only if you see here, which one you want to release. So I want to release everything except Fy. Only this reaction I want to get, because it will be supported on the roller, right? So here it is asking which one you want to release. So I want to release everything except Fx. If you see, this is Y direction, so this will not be released. Everything will be released. So I added a support. So what I will do, I will select this support and I will assign it pin support, and this support 3 I will assign here. You can see it is giving only this direction restraint. Okay, now let us go to loading part. First of all, the self weight of the beam we need to be calculated, the own weight of the beam. So I will go to load case details. I'll click on add. I will suppose create a dead load itself, load case 1, or you can change the name also. I'll keep it as load case 1. Add. I will add some load here. First of all, the self weight, own weight of the beam, and it is acting downwards towards Y direction. Okay, you can say opposite to the Y direction. So minus Y, so Y minus 1 factor. This is simply stat, those who know already knows actually. Add, and then I will apply a nodal load, so along Y direction, so minus 30 kilonewton. Why minus 30? Because Y is positive, plus Y is upwards, negative minus Y is downwards. So I'll click on add. So these are the two loads. Self weight will be applied to all the beams. So I'll go to assign to view. You can see the whole beam, for the whole all the beam, self weight will be calculated automatically, and I will apply point load. I'll apply a point load at this location. Assign to view, sorry, assign to selected node. Yes, yes. Okay, so this is my condition that I have created. If I just make it a bit different, control 2, because this is my beam. Okay, 300 500. Here I have a pin support, here I have a roller support, and at 1 meter I have a 30 kilonewton load. Okay, fine. So control 1, I should, this is my beam. Okay, correct. Now if I just go to analyze, I will define command as run analysis, add, perform analysis, save. So two warnings are there. What are the two warnings? Warning should not be there actually. Let me see what is the warning. Okay, the warning is there because I am doing 3D analysis, 2D analysis in a 3D space. So what I will do, I will change the utilities in command file. I'll change this space to plane, because I am doing 2-dimensional analysis, x and y, means suppose y and x, okay, or x and z. So this plane x and z, yes, it should be plane. Now this warning will not come. Okay, this is the instability warning. So run analysis, so no warning. Now I go to post processing mode, and for this load case I want to see the bending moment and shear force. So if you see here, Those who know STAAD.Pro will be understanding. Those not, you have to understand the first. You have to learn the basics first, that you may see other videos. So I'm just showing you how software is also giving the result. So now if I see the result, suppose for bending moment, okay, and if I just increase the this, it will not, it is not directly straight. There is some curve actually. If you see here clearly, it is not directly a triangle, right? There is some curve. So I should also draw this properly. Because of the uniformly distributed load, it will not be directly straight. So it will be something, curvature will be added actually, like this. So this you can, how this curvature is actually happening, you can find. Suppose if you calculate the point at this node, suppose at 1.5 meter, at 1.2 meter, at 1.6 meter, something like this, then you can find out whether this curvature is totally straight, like going linearly down. Okay, you do the calculation linearly. Suppose at 1 meter it is 23.75, at 0 it is 0, then how much it will be here. Or if you see at 3 meter reduction 0, at 1 meter is 23.75, so reduction is 23.75, then what will be at 1 meter. So this kind of linear equation you can find, and also you can find using our formula. If those two values are different, then you can say it is not directly linearly varying. It may be a kind of you can say parabola is being created due to the uniformly distributed load. I feel like there is a slightly parabolic curve I can visible. Now you can see the direction of the moment is opposite to our you can say direction that we have drawn. Actually, whenever, see here, our beam is bending like this. Okay, or I should say something like this. If you see here the bending deflection, so you can see how the beam is bending, something like this. Okay, so if the beam is bending like this, so this face is, if you see, this face is tension, this face is, top face is compression, correct? So I will be giving, that means the bending is happening downwards, so I will be giving tension reinforcement. When I will be designing the beam, I will be giving tension reinforcement at the bottom, compression reinforcement at the top if required, correct? Or there is no required, then I will not provide, because concrete itself will take the compression. But when you are doing the manual calculation, what we do, we draw the diagram in the compression phase. Most of the books, if you see, we draw the diagram because we consider that this is positive and this is negative component of, suppose, a graph paper, and we draw like this. Okay, but for our better understanding, where we have to provide reinforcement, suppose the beam is bending like this and you are drawing like this, so you will think that, okay, suppose for this bending moment, as it is top, I will provide reinforcement at top. It is wrong. Bending moment diagram is like this at the top, but we will provide reinforcement at bottom. So that's why in softwares, what they do, they give you can say bending moment diagram in the tension phase, where you have to provide the reinforcement. So here, as it is downward, so you'll be providing reinforcement for this downward at the bottom only, correct? So this is the reason behind this tension phase drawing and our compression phase drawing in the manual calculation. So I will see the result. I will go to beam result. Suppose I will see everything, annotate, close. You can see here at the bottom two ends I have 0 values, and at this particular point, which is 1 meter, right, we're getting 23.534. What is our result? We are getting 23.75. So this is something 0.25 difference we are getting. Okay, 0.25 difference we are getting from the manual calculation to our software result. Okay, because obviously there the stiffness of the beam is considered, a different method is maybe approached. So some very minute difference we can see. Correct. Now if you see the I don't think I don't know whether this diagram is parabolic. You please check with your manual calculation. I don't think it is parabolic, linearly only maybe, but this side it seems a bit parabolic because it is a long distance and we have both uniformly distributed. Mainly here, mainly in this zone, in this particular zone the uniformly distributed load is more governing. In this zone the point load is more governing. Okay, so that's why here some curvature we can see, so that you can actually check how it is coming. Okay, so here at the center of this particular part we are getting this value, at the center of this particular part we are getting this value. This is not required for us, we'll keep like this. Now if you ask me then how I will be finding out the moment diagram and what is the moment here, you just have to derivative ddx of the mx. Okay, now taking x equal to 1, x equal to 2 at the mx equation, you can see what is the value coming, then you can find out the diagram accordingly. I think this equation, is it the equation of parabola for this particular part that we are getting? I guess so. Let me see. If you see here, ax square plus bx plus sorry, if you convert it to just normal plus value, so ax square plus bx plus c. Okay, and the other equation you get ax square plus bx. Both are kind of parabolic equation only, but due to the, you can say, point load, we are getting kind of this kind of result. Okay, so it's very slight equation, sorry, slight parabolic curve you may see. Let me just cross check. Ax square plus bx plus c, sorry, plus c, equation you can say diagram. Okay, so this is a kind of parabolic curve only we are getting. Okay, yes, I forgot these things actually. So yeah, y is equal to ax square plus bx by c, it is a parabolic curve only. So that's why instead of drawing like this, I should draw something a bit, though I have not found the values, intermediate values, so it will be something like this and something like this. Okay, due to the presence of the you can say, due to the presence of the uniformly distributed load, though it is minimum, but a bit parabolic curve you will see in the big. Directly it will not go like this. Fine. So now these things we can solve. You can just check the equations of parabola and all, so you can easily find out. Okay, I forgot, so pardon me for this. Now if you see the shear force diagram, so you can see this is the shear force diagram. This is exactly coming what we expected in our you can say value. So you can see this is the shear force diagram. If you see the values also, very less difference, I guess. There will be, if I say ends, maximum, mid, annotate. Okay, so ends 25.301, we got 25.625, correct? So very a slight difference. At this point 8.233, I have got 8.125, very slight difference. At this point 15.301 and we got 15.625. Okay, so kind of similar value. If you see the diagram, diagram also kind of similar, values also very close to each other. Okay, just point difference we can see. Okay, so this is the way you can do this kind of manual calculations, and you can cross check in the softwares to verify whether you are getting the expected results or not. Okay, even when you are doing the design also, you can do the design manually, very simple design, and cross check the same in the software so that you can verify whether the software is doing it you can say the correct way or not. Okay, so in that way you can understand the methodology of the software, or you can say the process of the software also. Okay, that will be very interesting. So I hope you will find this session very it will be helpful. Those who are beginners, those who are already professionals, they may find it very boring, but I made it for the beginners only. I hope it will be helpful. If you have in doubt in this particular session, you can write me, or any other suggestions, opinions you want to share with me, please write in the comment box. I will try to implement your, or you can say try to implement your suggestion in my further videos. Thank you and see you in the next lecture.